Hi, this is Dr. Najib Balfakih. We are going to talk today about measurements, significant figures, and calculations. Why significant figures matter in chemistry? Because chemistry is based on measurement, and significant figures tells us how precise a measurement is. So, significant figures topic will help us to avoid false precision. We're going to also report answers correctly and compare labs data fairly and communicate results scientifically. For example, 2.5 gram and 2.50 grams are not the same level of precision. So assume that you are selling your gold and you went to a gold store, and only the gold store has in their scales only two sig fig, 2.5, only two sig fig, and your gold actually weigh 2.59, and 9 is not showing there, so you are losing your money. So the scale of 2.59 is more precise than 2.5. So when we talk about significant figures, we know exactly how many digits are included in our calculations. So our objectives today, you're gonna be able to identify the measurement and exact numbers, measured and exact numbers. Also, you count significant figures correctly, apply significant figures rules in calculations, and report answers with correct units. There are two types of measurement, qualitative and quantitative. In the quantitative, it has numbers such as the mass, the volume, the temperature. Uh, as qualitative is just describing the objectives, like what's the color, what's the odor, and what is the texture. So both types are essential for scientific analysis and reporting. Uh, but in chemistry here on this topic today, the focus will be on the quantitative data. In this semester, we're going to use SI units and base units in chemistry. The international system of unit provides standard units. We're going to use grams, not pounds. We're going to use for temperature Kelvin and Celsius, not Fahrenheit. In this course, we're going to use volume, and we have the glasswares, and we're going to use the mass as a measurement. Of course, we're going to use the scale and balances, and also we're going to use the temperature. As we said, we're going to use Kelvin and Celsius. Before we start talking about the significant figures rules, I would like to introduce what is the definition of precise and accurate. Precision, repeated measurement are close to each other, and accuracy, a measurement is close to the true value. It could be precise but not accurate. Let us look here. Precise, high precision, low accuracy. In this figure, so if it is high precise, the accuracy when it hits the target. So in our case, here it's not hitting the target. It could be somewhere here. So, but they are close to each other. Far away from the target, very close to each other. It could be even the same value, but it is not accurate. The other example is accurate, but not precise. High accuracy, low precision They are not hitting the target exactly. It is maybe in the second circle, but they are not the same value. Both accurate and precision, yes. All the arrows hit the target and to the point. And this example here, we have low precision, low accuracy. They are far away from the target. It could be hit here, 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 far away, maybe goes to the third round or the third circle. In chemistry, both are very important. Before I talk about the significant figures rules, I would like to talk about scientific notation. Actually, we use scientific notation to write the small, very small numbers or very large numbers. We use the format 10, the number times 10 to the power n. How we decide the number n? I'll give you the first example. We have 45,000. It is written 4.5 10 to the power 4. Why 4? Let us see here. 45,000. We assume the decimal point here, so we move it 1, 2, 3, 4. So we move it from left to right. Left to right, it is positive. So we move the decimal point 4 places. What about another example? Let me just erase this. And give you another example. When the power is negative. Okay, 0.0032. 0032. I'm going to move the decimal point to the right. 2, 3. So it is minus 3. 3 places. So key idea, the exponent tells how many places the decimal point. We could move it to the right, to be positive, to the left, and negative. There are 4 rules. Actually, all of these rules are concerned about 0. The rules define what are the numbers which are significant. The first rule, all non-zero digits are always significant. All non-zero digits. So example 1, 2, 3, there are 3 significant figures. Let us say, like if we have example 1, 2, 0, even or we talk about 0, 3, 2. So there are 1, 2, 3, 4, 5 significant figures. So all non-zero, all of the 0 in the middle, they are significant. Okay, let us move now. This is an easy rule, the first one. Second rule, zeros between non-zero, the digits are significant. So this is what I just gave an example. Actually, 0 between non-zero are significant. 101 is 3 significant. I just gave you an example. The third rule, leading zeros are never significant. So 0.0025 has 2 sigfig because the leading zero are not significant. By the way, we can write this as scientific notation. Let me do it here. Let us write this one as significant. Point, yeah, point, sorry, point 0.025. So let me write it as scientific notation. 1, 2, 3. So 2.5, 10 to the power minus 3. So look here, these are two sig fig. The power, 10 to the power, the powers of 10, we never count them when we count significant figures. So this is two examples actually. So leading zero are not significant. This is the third rule. Okay, let us go to the fourth rule. Trailing zeros after the decimal point are significant. Okay, so we have 2.50 has 3 sig fig. And this is a good example that we have leading zero is not significant. Also, trailing zeros are not significant unless if they came after decimal point. So let me give this example here. So 2.50, this is point, is 3 sig fig. However, 250 are 2 sig fig. Why? Because the trailing zero will never be significant. So 1000 is 1 sig fig. However, if we want to count these three zeros as significant, we can have decimal point at the end. So now you have 4 sig fig. Now we have 4 sig fig. If we add 0 here, without this 0, there's only one. Without this 0, there's only 1 sig fig. So these are the rules here. Non-zeros, all non-zeros are significant. 0 between non-zero digits are significant. Leading 0, they are non-significant. Trailing 0 without decimal point is not significant. Trailing 0 after decimal point are significant. Let us see the special case 1500. 1500 can be written here 2, 3, 4. Yes, this is a good example. I like it. 1.5, you have 2 sig fig. I told you that 10 to the power 3, all the powers are not significant. 1.50, this is the decimal point. This is the 0 after decimal point, so there are 3 sig fig. Here, the two zeros after decimal point, there are 4 sig fig. Exact numbers have unlimited sig fig. Exact numbers, like we say, I have 4 balls, so they are significant. 4 is 1 significant. I have dozen of pairs of shoes, so dozen is 12, so 2 sig fig. That's a good thing here. Let's go now. This is now we're going to start practicing. So how many sig fig here? Look here, the leading zero is not significant. So we have 1, 2. So actually the 3 zeros are not significant. So the answer has to be 3. Look at the second example. 5.060. How many significant figures here? If you say 3, which is not right. They are 4 because the zeros, the trapped 0, which is here, the one that I can show you here, trap 0, this is significant. Also here the 0 after the sig fig, after the decimal point, sorry. So they are 4. Let us see the other example. 1000, I told you before, trailing 0 are not significant. So we have 1 sig fig. 2.5. So we have all of these are significant. So this is 3 sig fig. Hopefully you answer the questions correctly. Beautiful. Calculation of significant figures. This is a very important slide. Addition, subtractions, answer has the same decimal places as the least precise measured. So if you add 12.11 plus 18.0. Now look here. The least precise measure is 18. So how many digits after the decimal point? So there will be only one digit. Yes. So you're going to follow the least measured. This is better measurement. It has two digits after the decimal point. So the answer will contain only one digit after the decimal point. So 30.1. This is the case of subtraction and addition. What about multiplication and division? Has same sig fig? Figures are the same with the fewest sig fig. So always in this case, in subtraction, multiplication, and division, also always the least will win. I'll give you an example here. 2.50, there are 3 significant figures, times 3.1, there are 2 significant figures. So the final answer has to have 2 significant figures, 7.8. So if you multiply 10 sig fig by 2 sig fig, the final answer only 2 sig fig. If you divide 5 sig fig by 3 sig fig, so the final answer will be 3 sig fig. Rounding rules. Round only the final answer, not intermediate in your calculations. No, I cannot remove my picture. Can I remove it? I don't know. So anyway, so we're gonna practice rounding again. I cannot move myself. Okay, let's go now. This is a practice problems. How many significant figures are in this number? Identify each digit and explain your reasoning. I will not answer it. You answer this time. So look here. How many sig figures do you have? You answer, and you'll tell me leading 0 is not significant, and 0 in the middle are significant, and trailing 0 are significant. What about the second one? Calculate 3.45 times 2.1. Hopefully, you're going to answer this question. I will not help you, but you answer it. When you explain, you're going to say the lowest sig fig wins. So you're going to have 2 sig fig. Also, this is another practice problem. Convert 45,600 to scientific notation. Look here, how many decimal points you're gonna move? How many decimal point? How many steps? 1, 2, 3, 4. Now you can answer it. Round this to 3 sig fig. Look here, this is a very interesting question. 4.5678. Can you answer it? You need only 3 sig fig. So you're gonna remove 7 and 8. You're gonna cancel them. But you cannot do that without rounding up. So 4.5. Then when you remove or you delete 7, here the fourth one, but 5 is higher than 5. So you're going to round the 6 to 7. So it will be 4.57. You're going to add these numbers. So 12.5 and 3.456. So you're going to add them together. But remember, the final answer has to have one digit after the decimal point, because always the least number of digits wins. I think we are close to end now. So this is a key takeaway. We talk about uncertainty, precision, and accuracy, and master your measurement. Great work. Thank you so much, and good luck, my friends.